All right, so we're recording now again. Oh, yes. 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 Yes, that Friday. Yes, they would be on the Thursday. That's the last day of class. So that's when you would present that Thursday, yeah. Thursday the 12th. The Thursday before finals week in the regular class. I mean, you have to come. It's your last class. It's a regularly scheduled class day. Yeah. Good? Yeah. All right, good. So yeah, so that's the project, hopefully. All right, guys. So now let's go back to the table of contents and we're gonna wrap up this module here and actually this module. If you look at this cross entropy module, it links to the same thing that I have in code here, which is the last of all of these files is cross entropy. Okay. But I just wanted to create its own module because I didn't want you to miss it. Okay. This is a really important concept that I think you should understand of how classifiers learn, right? So that's what we're going to discuss now. And that's cross entropy. So I'm going to click on this. Okay, here we are. And I'm going to open Colab just so that we can kind of see it in real time. Okay, so let's talk about cross entropy. Okay, so what is cross entropy? So, if we focus on just the two main problems of machine learning, we have regression, which is to generate real valued numbers. So, for instance, predicting temperature, what is the temperature in Fahrenheit given Celsius? So, if it's 0, then it's 32, right? So, it's a real value number. And we use MSE for that. But when we're doing classification, like we did with the GPT or we did with the ranking of the wine quality data, we want to predict, or iris, we want to predict for a sample of vector of 4, whether it's setosa, virginica, or versicolor, discrete, right? So that's a classification problem, and we use cross entropy for that. But we also use cross entropy for the GPT, the exact same thing, right? And it was a function. So what we're going to do today is we're going to try to understand it. Before understanding cross entropy, we're going to try to understand entropy. All right, entropy is from information theory, a metric proposed by Claude Shannon, right? And it's fundamental to everything we do, right? So it's extremely important. So let's take a look at cross entropy. So entropy is a mathematical idea describing uncertainty, right? So think of the cross of classification. In classification, we always say, okay, the label says this is a cat versus a dog, but we are uncertain of our prediction, right? We predict a vector where we say it's 0.6 cat, 0.4 dog. So there's uncertainty there, right? So we want to use this metric to kind of figure out and improve our model. So let's think of entropy, and let's think of the case of a coin, flipping a coin like we all know from probability. So given a very biased coin with both sides having a head, the probability of getting a head is what? 100%, right? Because both sides are heads. So there's no uncertainty there. Similarly, the chance of getting tail is what? 0, right? Because both sides are head. So in both cases, we are 100% certain of the outcome. The uncertainty is 0, and therefore we can say that entropy is 0. And that's the key thing. So that's the intuition, but there's a metric, a formula that we can use called entropy, and it helps us to model exactly that. So given a fair coin with head on one side and tail on the other side, we have reached the maximum uncertainty about the outcome. Do you see that? It's a fifth. We always say it's a 50-50 chance, right? So because it's got a head on one side and a tail on the other side. And the entropy in this case is the highest. We just don't know. Now the entropy formula is going to be this, just that. So it's a sum of the probability of outcomes, right? So these are going to be all possible outcomes. So for instance, for a coin flip, there's two outcomes, right? And so it would be, notice that there's a negative term in all of these. So it's going to be negative P of that outcome times the logarithm of P plus the negative P of that other outcome times the logarithm of the probability of that other outcome. Okay, so this is the formula that we use. There's going to be binary, and then there's going to be multi-outcome scenarios. For now, I'm starting with binary, and we're going to end up wrap up with multi-outcome. But it's just an extension of this formula. So the entropy formula is this: the sum over all potential outcomes. And P is the probability of those outcomes. Okay, so let's make this mysterious equation into something very clear that we understand, which is, some Python code. All right, so let's go ahead and get some libraries going. None of this involves like PyTorch or anything. This is very Python from scratch, NumPy. So let's add the libraries here. Whoops. All right. And here is, if you notice, that same equation. So for the binary case. So this is the equation for the binary case. Notice you only need to provide one P because it's a two-class problem, binary. So one P and then the other one is just 1 minus P. Right? So if I'm flipping a coin, right? So it's 0.50 of head, 0.50 of tail. So 0.5, 1 minus 0.5, also 0.5. All right, so notice here also, this is added because I'm going to be plotting this, and probabilities are only going to be between 0 and 1. So all other values, let's just ignore them by giving them a 0. So you can see here, the probability of two outcomes is just going to be negative. This one is also negative, makes the plus negative, and it's going to be P times the logarithm of P, and this one is 1 minus P times the logarithm of 1 minus P. So it's the same probability here and here. Okay? Got it? All right, so that's the equation, the formula over here written as a function. So we add the function in here, and now I'm going to prove to you guys that this whole thing I was saying is true, right? So of flipping the coin and everything. So the point is, this formula captures what I just said exactly. So let's go ahead and grab this. And this is just me creating a plot of values between -2 and 2, but in the range between 0 and 1, which is the probability, we're going to see that behavior that I was discussing about where's the uncertainty. So if you notice here, I just create a range of values, then I create a list comprehension of these values, running them through the function. So every single value in X, right, from -2 to 2, is I, and I'm running it through the entropy function that I just created to compute entropy. So here I'm computing entropy, and then I'm just going to plot it. Okay, so here we are. And there you go. So you can see here, this is the probability of head, and this is the entropy, right? The formula captures it perfect. So if the probability of head is 0, what's the entropy? 0, right? If the probability of head is 1, what's the entropy? 0. Do you see that? But sometimes we're going to have a situation where the probability is like 0.2 to 0.8, right? And you can see the entropy there. It's not quite the highest, because the problem is, if I know that I have a 0.3 to 0.7 probability, well, one case will happen more than the other, right? So I have less uncertainty. But the maximum case of uncertainty is when the probability of head is 0.5. right? Because then we have the other outcome, which is tail. So there we have the highest entropy. Do you guys see that? So this equation captures perfectly that behavior that we discussed. Okay, that's just entropy, not yet cross entropy. All right, perfect. So we did that one. So now we can take a look at this. So the top has the least certainty, which is the same as saying the highest uncertainty, right? So at y equals 0, you have the most certainty. Where both sides are head and p head equal 1, then the uncertainty is 0. When both sides of the coin, when both sides of the coin are tail and p tail equal 1, the uncertainty is 0. The entropy is highest when the coin is fair and p head equal 0.5, as we just demonstrated. Okay, so again, the important thing is that function does indeed work, right? That's the key thing. And that function is the foundation of so much in machine learning. That is very amazing. All right, so let's look at two examples of this, and we can corroborate one or two. So here we have one example. Calculate entropy for a coin with both sides as head. Right? So p head is 1 and p tail is 0. So in this case, you can see we just do, because it's a binary problem, we have negative 1 times logarithm of 1 plus negative the other probability, 1 minus 1, which is 0, times the logarithm of 0. Do you see that? And if we compute this, the entropy is 0, which translates exactly to what we wanted because there's no uncertainty. You see that the metric works really well. The other example, because machine learning is not going to create a graph, right? So it's not going to create a plot. It needs to use the formula. So example 2, entropy for fair coin, so that p head is 0.5 and p tail is 0.5. This has the highest entropy and maximum uncertainty. And notice I'm using logarithm 2 instead of for the actual computation. So here we do the two cases now, which are both 0.5, head and tail, two outcomes. So then notice negative 0.5 times logarithm of 0.5 plus negative 1 minus 0.5 is also 0.5 times logarithm of 0.5 gives you entropy of 1. And anything in between will be reflected by this. So anytime we're trying to optimize for, let's say, the highest entropy, or then we could use that formula and it would basically live in this figure here. Got it? All right, good. So that's entropy itself. So here we can run this one using the same formula just to demonstrate that it does work. Okay, so the value is 0.5, goes in, and that gives you 1, right? And that is the entropy value. All right, so now that you understand entropy, I'm not hearing any questions, then we can move on to just the extension, which is a slight extension of what cross entropy is. So cross entropy, the word cross just means that now there's two things going on. Before we had the same probability P times ln P, right? And now it's like we're going to have predicted P logarithm of real P. You see that? So it's this. So we're just going to make that slight change. So cross entropy here now can be considered a measure of the uncertainty of outcomes due to a mismatch between actual likelihood of outcomes and what we think this likelihood is. So it's the comparison of two probability distributions, the probability distribution of the real thing and then of the perceived thing, what you're trying to predict. So it can be considered a measure of uncertainty of outcomes due to a mismatch between actual likelihood, think of this as the real data of outcomes, And what we think is the likelihood, think about our predicted. You see that? It's what we think it is. It's our predicted. So consider, if we think a coin is fair, but it is not, so that's what this is capturing. This is like the key thing, right? So if we think a coin is fair, but it is not, then we will be surprised by the outcome. And that's what cross entropy essentially is, what they invented, right? So if we think a coin is fair, but it is not, then we will be surprised by the outcome. There will be uncertainty about that outcome. If you think the coin is fair, and it is indeed fair, then you will not be surprised. As such, it will have a low entropy. When does this happen? When I'm predicting cat and dog, 1, 0, right? And in the first one, I think the coin is fair, but it is not. My prediction was not 1 and 0, it was 0.6, 0.4. Do you see? So what happened there? I was surprised because, we thought it was fair, but it is not. Okay. Now, the other case, if you think the coin is fair and it is indeed fair, then you will not be surprised. When will this happen? Cat and dog, 1, 0. And guess what? My prediction, 0.98, 0.02. Do you see how I'm less surprised here than in the other case? And that's exactly what cross entropy is doing. Okay, so it's comparing the real and the predicted. So if we think a coin is fair, but it is not, then we will be surprised by the outcome. That's cross entropy. There will be uncertainty about that outcome. If you think the coin is fair and it is indeed fair, then you will not be surprised. As such, you have a low entropy. And that's the key. That metric captures this very nicely. So we think of cross entropy as a comparison between two probability distributions. The more they match, the lower the cross entropy. This is like when somebody was inventing machine learning, they were like, wait a minute. The more they match, the lower the cross entropy. That's exactly what I need to do. I need to optimize so that cross entropy is low, because that means the two probability distributions are matching more, and I'm less surprised. Do you see that? So this existed before, and then it was adapted to machine learning as a loss function. So an exact match is equal to 0 cross entropy. So cat 1, 0, your prediction 0.99999 to 0.00001. It matches almost perfectly. And whenever you do this calculation, the loss is going down. And that's exactly what you want. Okay. So an exact match is equal to 0 cross entropy. In neural networks, the predicted outputs are a probability distribution. We've discussed it many, many times, right? Softmax, right? Makes them add up to 1, makes them a probability distribution. And the real outputs are also a probability distribution. Sure. Cat, dog, bird, 1, 0, 0 adds up to 1. It's a probability distribution. Don't think that it's just some discrete thing. It actually has this meaning. So now that takes us to cross entropy. So cross entropy is exactly like the other one, but instead of just having the probability of the outcome, now we have the probability of the outcome when it's real and the probability of the outcome when it's the predicted. Because you remember, our model is trying to predict, and we have the real labels, and we're trying to match those up. So it's the exact same equation, but this has changed. So it's the sum of outcomes of the probability times the logarithm of the probability, but you compare the real to the predicted. And that's like saying what you expected versus what you got, which is where cross entropy comes from, which is what I said over here, going back to, if we think a coin is fair, but it is not, then we will be surprised by the outcome. You'll take a probability course, they'll talk about this without tying it to machine learning. But that's where it's coming. It's probability theory. Does this make sense, guys? Because that's it. I mean, that's cross entropy. So then all we have to do now is compute given the values of real and predicted. And I have an example for that. So first, I'm going to do the binary, as I said, and then we're going to extend it to multi-class cross entropy. Okay. Now in machine learning, this works because you guys are experts in tensors now, right? And you understand everything is really a vector or a matrix. So there's no need for a for loop of adding values, given that you have a vector of values, right? So all values are in that vector. So let's take a look at an example here, a very simple one. I have the case where the real label is 1 and my model is predicting 0.90. Remember that in classification, we're predicting essentially type of probabilities, right? The probability that is this class. 0.98 cat, 0.01 bird, 0.01 dog. Adds up to 1. So here my model is predicting 0.90 cat, and it is 1 cat. It's good, right? You would argue it's good. So let's look at what cross entropy does here. So cross entropy, you take the real and the predicted. So it's for the outcome. So my negative 1 times logarithm of 0.9, right? That's the case. Plus negative, the other outcome for the binary is going to be if this is 1, then the other one is 0, 1 minus 1. And this is logarithm, again, 1 minus 0.9, 0.1. Do you see? So the other outcome. So it's either 0.9 or 0.1. So when you calculate this cross entropy, the value is 0.10. Do you see that? That's a desirable outcome. You want that, you're minimizing cross entropy. And when you minimize cross entropy, the predicted is getting close to the real. Now let's look at the opposite case example. The real is 1, cat. But for that category, my model is only predicting 0.10. Do you guys see that? So not a very confident model, right? It might actually be saying, let's say it's a 2 vector. So it says 1, 0, but it's saying 0.1, 0.9. Not good, right? It's not matching. It needs to be flipped. But let's see if the cross entropy catches it. So cross entropy then, when the case is 1, the probability is not like the previous one where it's 0.9. It is actually 0.1. Do you see that? Plus negative 1 minus 1, and the opposite of it is 0.9. When we compute this, 2.3. So do you see, when the prediction is bad, the cross entropy is higher. As the prediction gets closer to the real, look at what happens to the cross entropy. It goes down to 0.10. So by minimizing this formula of cross entropy, we are essentially achieving our objective because we're changing the weights, right? Via stochastic gradient descent, the weights are changing. So initially when it was training, it was just predicting 0.1 with that set of weights, and loss was 2.3. But its objective is what? To minimize that loss. So what did it do? It kept changing the weights, until eventually the predicted was 0.9 compared to the real, which is 1. And guess what? That is reflected in the cross entropy loss function. So you optimize, you minimize it. That's your goal. That's your goal. The weights need to be changed so the model generates a value, and when you compare it, this needs to go down. Does this make sense, guys? Any questions? This is the essence of cross entropy and how it works. Graphically, and this is kind of important also, so this is the case for real equal 1. So I'm going to show it over here. Okay, so this is the same formula, as you can see, but now notice I have changed it a little, right? So before the formula had P and P, right? Do you see that? P and P. Now the formula has changed where this will have the real 1, let's say, and this will have the predicted value itself for the comparison of cross entropy. So now we're going to give it, when we invoke this entropy over here, Notice that we give it all the values, but we're assuming that the goal is for it to be a 1. Okay, it's got to be that for that cat 1. What is this value for cat? Okay, and this is, for the binary case. So I'm going to run this one, and this is what the graph looks like. So what's important here to understand is that equation translates into some graphical representation. But really, the equation is what the machine learning model is optimizing, right? But there's an intuition here that is where the name stochastic gradient descent comes from. If you look, you can think of this as what? Like a mountain, and you're going downhill or uphill. Do you guys see that? So in the algorithm of stochastic gradient descent, you're trying to optimize this cross entropy, right? And that cross entropy graphically can be represented like this. So so you notice on this axis is entropy, and on this axis is the probability, which is determined by the weights of the model. So the way to think about this is if I'm here, right, and I'm updating the weights of the model, right? So the weights of the model give me this entropy. Do you guys see that? That 0.9 versus 0.1, right? They determine that I am here graphically. So in calculus, when you have a function, what we say is that if we take a derivative of those, a partial derivative of those weights on this function at this point in time, it's going to tell me the slope of this function. And that's where the name gradient descent comes from. You want to descend. Why do you want to descend? Because you want the lower entropy. So if I'm here, it's going to tell me that I should go to the right. Do you see that? I'm here. Imagine I'm a little person, and I'm going to take a step. So should I take a step to the left, or should I take a step to the right? Which way takes me to the bottom, the lower entropy? Going to the left, going to the right. But do you see that this function, like, you only live in this universe? That's what you have to understand, is that function just creates this line. And the machine learning algorithm only lives there and nowhere else. So it can either go to the left or the right. Got it? Yeah, go ahead.
This is where that's set.
Beautiful. So remember how I said the gradient descent just gives plus or minus, right? But what about the size of the step? Well, that's the learning rate. So if you put a learning rate that is 0.00000001, what's going to happen? You're going to do this. After 1,000 iterations, you're still just right there. Now, if you give it a learning rate of 0.5, that's a really high learning rate. What might happen is this. Really big steps, which may not be a good thing because this is a simplified example. And remember, you have tons of weights, so you don't want to overstep too much. Yeah, good.
But here, that can change the prediction itself. You want to change the weight from top.
Right, exactly. So there's two functions. Remember, the loss function and the inference function. So the loss function produces the y, and then y is in here, right? So remember that, where did I have the equation? Oh, this is my Jupyter. That's a good question. So let's see, where was it? This. Y pred, that probability, is what? That's your inference function. Y equal W times X plus B is predicted, correct? Well, you can replace this one, Y pred, and plug in there Y equal WX plus B. So that value, as you're changing the weights, that value is changing. So the loss function contains inside of it the inference function. That's actually, it shows me that you guys are not reading the notes that I gave you, because in the node, I have that plugged in there, but it's a good observation. So let's go over here. Let's go to chapter 4. So you know, Wx plus b, right? That's actually this one also has it. In the regression, you see how y minus y hat in regression, I'm plugging in the inference function. So in the cross entropy, should be in there. Here. There it is. Here is the actual equation. Do you guys see it or no? See how it's y times log of h, 1 minus y log of 1 minus h x. What is h? H theta, when you see a theta, that means it has parameters. So h theta, you can see I kind of wrote it this way. So I have a log of h theta and a log of 1 minus h theta. But here it's expanded to be log of g of w times x, 1 minus w times. I didn't include the bias in there. But do you see what I'm saying? So this here is y equal wx plus b. So when you change the w's, you're effectively changing the resulting value there and you optimize. Yeah, go ahead. So, but just to kind of elaborate, this here probability of head is what? The y. But that depends on x times w plus b. So however I manipulate the w's results in manipulating probability, which results in me moving up and down this thing. Do you see it now or no? Do you all see it? Pretty important that you see this. Yeah.
Point 6. You know that we have to increase that prediction.
Yeah, you want it to be 1. Yeah, because remember, you're wanting the model to be very certain that it's a cat. So 0.99 is more certain of being a cat, and that's closer to 1. Yes. Right, exactly. But that's what stochastic gradient descent does for you, because you don't randomly update the weights, which would be equivalent to me saying, you know what, I'm going to go up. Now I'm going to go down 3 times, and now I'm going to go 7 times up. You know, no. In fact, it's like a mountain, and that's why it's called stochastic. Stochastic just means like randomness. Gradient, which implies like a mountainous thing, like a thing going down. Descent. You're always going in descent, right? To why? Because by descending, you're lowering entropy. But see, this is just like humans invented this to understand this graphically. The computer does not create a chart and look, it just does calculus on the functions. But intuitively, it comes from there. So again, if I'm over here, right, what does that mean? I have, I want to be at 1, right? And so I need to go down to reduce the entropy. But how do I go down? By changing this value of probability needs to change, but this value is dependent on W plus X plus B. So the weights change, and so if I went over here, it's like a bad loss or something, right? So then the model gets that feedback to do the optimization so that it goes like that until. Now this is for one example. Remember that there's tons of variables, so there's some kind of a six.
There's some point where it just side slopes it up.
It could
It's not constantly updating the weight that it's already.
This is a great point actually, and this I can't really say that there's This is a highly researched area in machine learning. Neural networks, this is a simplified understanding of it, which is true for one case, but there's tons of variables that need to be optimized. So what happens is graphically, instead of being a mountain like this, it's a landscape of valleys and hills and things like, no, it's true. So what happens is your weights fall, and sometimes they can go to a very deep valley, but there was a deeper valley over here. And so there's a term in machine learning and optimization called local minima and global minima. So the global minima would be the minimum of this whole thing. But why do we start the weights randomly? So the intuition, again, if you have this mountain range, think of like an airplane dropping paratroopers in parachutes, right? They're going to fall in different areas of this range governed by these functions. So that's why we want to do this as randomly as possible so that they fall, and hopefully one of them will fall in one of these valleys, because if they do fall in one of these valleys, stochastic gradient descent guarantees it'll go down. But the problem is they may fall in a higher one, and they never fell in this one that goes down. Do you see that? Right. No, right. I mean, there could ChatGPT could have a Mariana Trench that no one has found yet. Can you imagine if we found it? But stochastic gradient descent can't really go that far because it's very trial and error. So there are limits. Like if it falls in one of these, it's going to say plus or minus. What gives you that? Calculus. Newton invented this. There's a function. He can take the derivative of it, right? And it puts a tangent on it, and that just gives you plus or minus. This is 1700 mathematics. And then they just applied it to this. Yes. This line here is the loss. So think of the loss as a universe that's very strict. The values cannot live here or here. They can only live in this blue line for that variable. But this one over here, probability of a head, is the y. Because we are trying to predict the probability that it's a cat. We say it's 0.20 cat. That's what we're saying here. But what determined that 0.20? Well, 0.20 is equal to W times X plus B. That's the inference function, yes. The inference function is always W. It's a neural net. That's what we've been stressing all semester. You saw a GPT, still WX plus B. So the key is the W's get updated, right? How? Every single W, right? You grab it and then you minus or plus learning rate times plus or minus. And you update. Every single one of them has to be updated that way. At some point later, we'll discuss that little part. There's something called the chain rule in calculus and all that, because you're not just doing one, you're doing 7 billion, right? And individually for the layers is back propagating. But this is a key thing. Two functions working together. The loss function creates this very hard rule. And then the weights determine where this probability moves up or down. And obviously, because you're here and your goal is to go down, so every time it's like you're there at that point and you measure, what's my slope, right? And so on. Does that make sense? Okay, perfect. So the other one, the last one, and we're almost out of time. So is this one. The other case is 0, right? So you can think of it as if the probability is 0, right? That's where we get the lowest entropy, the other case of 0, then the graph would look like this. And so, again, notice this is, do we go left or right here? left the other direction. Do you see that? So calculus, the derivative, will always give you to go in that direction. Do you guys see that? All right, and so what's important about this is sometimes in the equation, we had a situation where it's 1 and the other one is 1 minus 1, which is 0, right? So we would have either a 0 case or a 1 case. So essentially, now that we have this open, you can see that this is the equation, but there's two graphs involved, because when the value is 1, this becomes 0 because it's 1 minus 0 and the whole term becomes 0. So then the graph is just this little function here, y equal 1. So it looks like that. So that's what governs the universe for that case. Make sense? And then when it's the other case, y is equal 0, right? So this whole term becomes 0. This is 1 minus 0, which is 1. So this term, it becomes alive. And y equals 0 then is this case of the graph. So now it is, even though that equation really has both graphs, it only looks at one or the other, right? And that is stochastic gradient descent. You know, this idea that it's governed by this, and then by plus or minus, we decide how to go down in the slope or the gradient. All right, so we have 3 minutes, so let's kind of quickly go through multi-class cross entropy, but it's just an extension. So here I have 5 classes. So as an easy way to understand the multi-class cross entropy loss function, or the way to understand it is with an example. Assume we try to classify images of vehicles, and we have 5 categories: plane, car, boat, bike, and balloon. Given a cross entropy model, so now I'm extending it to multi-class, right? So this is Iris, MNIST, GPT. This is actually the case that most of the cases we do. Assume we try to classify images of vehicles. Given a cross entropy model, we have the following output vector for this multi-class problem. So we have Q1, yeah, which is 0.3, 0.20, 0.05, 0.5, and 0.40. Do you guys see that? So this is what the model is predicting for this multi-class. According to this model, the image is 30% plane, 20% car, 5% boat, 5% bike, 40% balloon. The model is not very confident about what type of vehicle it is. In contrast, the label distribution for each image would tell us with great certainty 1, 0, 0, 0, 0. So this is a plane, right? Do you guys see that? Well, now let's see if cross entropy truly works. So this tells us that this is a plane. We can calculate the cross entropy to measure our model's cost. So here we are. Remember, it's the same formula, just different letters. P and Q. P is the real, Q is the predicted, essentially. So now, how do we do the computation? Well, it's going to be 1 times log of 0.3. Do you see the 0.3 there? Plus 0, because it's a 0 here, times log of 0.20, and so on for all of them, right? There's uncertainty. When we do this calculation, it gives us 1.20. Our goal is what? Cross entropy should go down, right? So we try another set of weights, but informed correctly by stochastic gradient descent. So after training, the model is much better, and it can predict the following: 0.98, 0.01, 0.01, 00. So now, as you can see below, the cross entropy is computed by 1 times 0.98 plus times 0 times log of 0.01 and so on. And notice that the result is 0.02. So cross entropy, what are we trying to do? Minimize it. Well, we update the weights, and when the weights give us something that looks like this, which reflects the labels, then that's where we get the lowest value. Therefore, with the cross entropy loss, you compare predicted values to the labels. As the predictions improve, the cross entropy value goes down. That's it. What do you guys think? Pretty amazing, right? This is a very important piece of of ideas of math, and as you have seen, ChatGPT uses this. All right, so this is cross entropy. We will come back actually later to MSE, much simpler and intuitive, but similar ideas. We'll have that discussion, which is some of the next modules coming up. All right, guys, so it's exactly 9:20 actually. We are done with this module, and then as I said, NIO next week, and then also some additional ideas, theoretical ideas of this. Okay? All right. Have a great weekend and Thanksgiving. Yeah. Oh yeah, Halloween. Sorry.